All right, let's dive into one of the most powerful algorithms out there. It's one you've probably never heard of by name, but trust me, it shapes your digital world every single day. So our story actually starts with a pretty simple question, one that's almost impossible to answer. Back in 1946, a brilliant mathematician, Stanislaw Ulam, was recovering from an illness. He was playing a lot of solitaire, and he got to wondering, what are the actual odds of winning a random game? Well, the number of possible games is 52 factorial. And that is just a ridiculous number. We're talking about an 8 with 67 zeros after it. I mean, it's so vast, so astronomically huge, that trying to calculate the odds directly, it's completely hopeless. A supercomputer would be crunching those numbers for longer than the age of the entire universe. So Ulam has this flash of insight, this light bulb moment. He realized, okay, calculating the exact answer is impossible. So why not just simulate it? You could just play hundreds, maybe thousands of random games, count how many you win, and boom, you've got a pretty darn good estimate. It's just a beautifully practical solution to a problem that's otherwise completely impossible. And this revolutionary idea, using randomness and just repeating a simulation over and over to solve problems that are too hard to calculate directly, well, that became known as the Monte Carlo method. And the name? It's a fun little nod to the famous casino his uncle used to go to. Because really, at its core, the method is all about using the logic of gambling to find answers. Okay, but here's where things get really interesting. This whole simulation idea, it hits a massive wall when we start dealing with deeper, much more common problems in modern stats and machine learning. I mean, what do you do when the problem is so complex you can't even generate the random samples you need to start the simulation? This kind of thing happens all the time in Bayesian statistics. See, a lot of the time, we can describe the shape of the answer we're looking for, this thing called the posterior distribution. But to actually pull random samples from it, we need this one specific number, a pesky normalizing constant, as statisticians call it. And guess what? Calculating that is often just as impossible as the solitaire problem. So yeah, we're stuck all over again. The solution, believe it or not, comes from a totally different field, from work pioneered by Andrei Markov. He was studying something that sounds completely unrelated, the sequence of vowels and consonants in Russian literature. And he found something really profound. The next letter in a word isn't totally random. It actually depends on the letter that came right before it. He showed that even in a system where events are linked together, a chain, these predictable patterns start to emerge. And this is the absolute genius of Markov Chain Monte Carlo, or MCMC for short. It smashes these two big ideas together. What it does is create a special Markov chain of samples that lets us explore this whole landscape of possible answers in a really smart way. So instead of just sampling blindly, it takes what you could call a purposeful random walk. It just naturally starts spending more time in the areas where the answer is most likely to be. And the best part? It does all this without ever needing that impossible constant. So how does this thing actually work? Let's walk through one of the most famous MCMC algorithms. It's actually pretty simple. First, you start at a totally random point. Second, you propose taking a random step to a new point. Now, here's the clever bit. Third, if that new spot is uphill, meaning it's more probable, you always move there. But, and this is the really crucial part, if the new spot is downhill or less probable, you don't automatically reject it. You might still move there based on a certain probability. It's that little feature that lets the algorithm explore the whole map and not just get stuck on the very first hill it climbs. And finally, you just do this again and again and again, thousands of times. And this little snippet of pseudocode really illustrates the core logic perfectly. I mean, look at it. It's just a simple loop that goes on and on. Propose a new spot, check if it's a better fit, and then decide whether to move or stay put. You let that simple process run for thousands of iterations, and what you get is a beautiful collection of samples that represents a distribution we could never, ever have figured out directly. And this idea, as simple as it sounds, has had an absolutely monumental impact. I mean, it started out in the 1940s as a top-secret tool for the Manhattan Project. Ulam and the legendary John von Neumann used it to figure out critical physics for the atomic bomb. Then, fast forward a few decades, and it becomes the literal foundation of the modern internet. Google's PageRank algorithm, that's just modeling the entire web as one gigantic Markov chain. So yeah, from top-secret physics to the very heart of the internet, and that journey brings us right up to today. And today, it is right at the absolute cutting edge of AI. This plot here from a paper called Q-Align shows how researchers are using MCMC-based methods to align large language models.
Basically, they can fine-tune a model's answers on the fly as it's generating them. And the results are amazing. It consistently reduces errors and actually outperforms other, much more expensive training methods.
So, does all this mean MCMC is some kind of magic button? You just press it and get the right answer to any problem you can think of? Well, no, not quite. It turns out there's a real art to using these methods correctly.
Yeah, as the great statistician Andrew Gelman puts it, just running the algorithm for a super long time isn't a fix for a bad setup. If your sampler isn't working right, you could run it for a zillion iterations, as he says, and all you'll get is garbage. You've just wasted a whole day of computing time for nothing.
So you really have to diagnose if your chain is actually working. Take a look at the image on the left. That's a chain with what's called poor mixing. The sampler is just getting stuck in a few spots and isn't exploring the whole space. That's bad. Now look at the right. That's what you want to see, a well-mixing chain. Statistician Chris Vonsbeck has this great name for it. He calls it a fuzzy caterpillar. And when you see that, you know your sampler is healthy and happily exploring the entire landscape. And it's a surprisingly delicate balance to get right. In fact, there's a lot of theory on this, and it shows that for some of the most common MCMC algorithms, the sweet spot, the optimal rate for accepting new steps, is right around 23.4%. Yeah, that's specific. It can't be too high, can't be too low. It's like this little Goldilocks zone you have to hit to make sure the chain is exploring as efficiently as possible. So when it comes right down to it, MCMC isn't magic. We absolutely can't treat it like some kind of black box. Its success really hinges on the person using it making smart, careful choices. You've got to design a good model, pick a smart way to propose new steps, and always be checking the output to make sure you've actually found the right answer. I mean, think about the journey here. From figuring out the odds of a simple card game, to building the most destructive weapons in history, to powering the entire internet, and now shaping the future of AI. This one elegant algorithm has consistently given us the keys to unlock problems we once thought were completely impossible. It gives us a way to find answers when faced with just staggering complexity. So the real question is, what unmeasurable problems are we going to solve with it next?